Okay, so we're going from the revolutions that we did with disks. We took a step away from that to do cross sections, and now we're coming back to revolutions. Okay, and the revolutions that we're going to do here are going to be that scenario. And in fact, if you were taking notes and you have that flow chart that I started talking about, if you could pull that out, we're going to add to that. The flow chart I'm talking about is the questions. Okay, is the representative rectangle horizontal or vertical, that whole business. You got that somewhere? Okay, so now we're going to address the branch that says, is the representative rectangle perpendicular to or parallel to, and we're going to handle the parallel branch. And it's an easy branch. It's real simple. If it's parallel to the axis of revolution, that leads us to do a shell. And by the time we're done with the lesson, I'll have a formula for you to fill into that chart, and that'll complete the chart for you. So you have this nice flow chart to handle all these problems. It's going to become relevant because on the assessment, for these problems, it's been very simple. Find the volume of this thing using disks. Find the volume of this thing using cross sections. On the review and the assessment, you're going to be introduced to problems that are going to say, here's a solid that's revolved around this axis. And you're going to have to decide which method is easier to use, disks or, disks/washers or shells. I personally will try to use a disk or a washer whenever I can. You'll see why in a little bit. But there are some problems where you're just going to absolutely have to use a shell. Okay? So let's talk about shells, get this wrapped up. Okay, so like I said, we're going to use the shell method. We're going to have to compare the two uses. So even on tonight's homework, you'll see a little bit where here's a problem, do it as a disk. Here's a problem, do it as a shell. Which one's easier? Similar to what you did with do it with a vertical rectangle, do it with a horizontal rectangle, which one's easier? And then today, I think it's important that you be able to perform CPR. How many people can do CPR? Excellent. That makes an old guy like me feel better. All right, so here we go. Let's go back to this sketch pad thing and look at this case. Okay, so down in the bottom here where it says shells, now all of a sudden I've got a representative rectangle that's parallel to the axis of revolution. And when we revolve it, whoa, that's what I meant to do. There we go. We get that. And that's called the shell. Okay, so let's talk geometry. How do you find the volume of that thing? Go, Kev.
It's a cylinder, so you just find the volume of the bigger cylinder and then subtract it minus the smaller cylinder.
Good. And that smaller cylinder is actually the hole that's punched through it.
Yeah.
Right. Perfect. Okay. So we're going to build on that process and turn this simple, I shouldn't say simple, but yeah, simple geometry problem into a much more complicated calculus problem. Okay, but not too bad. Okay, so then, we got all that fun stuff. That's really all I wanted to show you is what that looks like. So let's go back to this slideshow. There's our shell. And there's a lot going on in this shell. So if you want to try and take notes on this, you can. If you just want to put your writing utensil down, that's okay too. What I'm going to show you is where the formula comes from. What I would recommend is just being a mathematical sponge. Just sit there and absorb information. Trying to keep up with this is going to be too crazy. If you do want to go back to it, I'll post a slideshow like I always do. I'll post a video. You can go back and copy all this down. Okay? So we're going to play this whole thing off of what Kev just described. We're going to take the volume of the big cylinder, the whole thing. We're going to find the volume of the hole punched through it and subtract the two. And to do that, in this picture, I labeled a whole bunch of different distances. So for instance, h is the height of the cylinder. That's easy. We'll come back to delta r in a second. We've got R1. R1 is the distance from the center out to the outside radius. R2 is the inside radius. And R is the distance halfway between. Okay, so we'll come back to that. There's a lot going on here. This first line is what Kevin described. This is the outside cylinder minus the hole. The rest of the stuff I did from that point on is all some weird algebra to get me where I need to go. And I wouldn't expect you to be able to do this, but like I said earlier, I think it's important that you understand where this comes from. Second step, I factored in a common factor of a pi and an h. That leaves me with r1 squared minus r2 squared. That's the difference of perfect squares. And so from Algebra 1, you remember that that can be factored into r1 plus r2, r1 minus r2. Then a 2 and a 1/2 magically appear. Why did I do that? I'll show you in a second. I needed a 1/2 in there. I can't just randomly put in a 1/2, so I also included a 2. Now, the reason I need a 1/2 in there is because I want to talk about this thing. I needed that expression. 1/2 r1 plus r2. What is that? Add up two numbers, divide by 2. What do you end up with?
Average.
It's an average. Right. So that's the average radius. That's little r in the picture. It's the distance from the axis of revolution to the center of that shell. Okay. So we then talk about r1 minus r2, this thing being the thickness of the shell. Now this is calculus. What am I going to want to do with the thickness of that shell? Anybody?
Use it as dx.
Good. Which means what's going to happen to the size of it?
It's going to get really small.
It's going to get really small.
And it's going to be infinite?
Infinitely small, right, Allie?
Yeah, because the dx makes it...
Good. Okay, so now we get into some concepts here. In a geometry sense, calculating the volume of this shell is all of this gunk. Okay, in geometry, you wouldn't go through the hassle. You just do what Kevin said and take the big minus the small. But now that calculus is coming up, we want an accurate answer. We want as accurate an answer as possible. So we're going to shrink the thickness of that shell down to 0. And that's where this dx comes into play. So delta r isn't an acceptable answer for us anymore because delta r would actually have a value. Okay, I could have a shell that's a 0.5 centimeter thick. I could have a shell that's 1/8 of an inch thick. We want that shell to get really, really, really skinny. Okay. Almost 0, which we call dx. You take all that conceptual gunk and you put it together and we get this monster. This is what we're going to do to solve most of these shell problems. Okay, this 2 pi is just there as a byproduct of all the stuff we did on the previous slide. The area of the rectangle comes about from all the other stuff, the average radius and the delta r. And then the distance away from the axis is how far is this shell away from the axis of revolution. So things like top minus bottom and left minus right still come into play here to find out those values. Okay, so we end up with that monster. Okay, now, how did I make the transition from here to here? Okay, well, that x represents the distance away from the axis of revolution. How far is that representative rectangle from the axis of revolution? F of x times dx is going to be our area of the rectangle. So these are things that we've done before as individual components, but putting them together, we get this bizarre shell thing. It also becomes very confusing putting all of this together because you'll recall from discs and washers That wasn't a 2 pi, it was just a pi. Now with shells, it's 2 pi. With discs and washers, it was pi r squared. This is x times f of x ds. So it gets a little confusing. Okay, questions so far? So all of that gets us to this thing. And some of you are just going to say, okay, I'm going to recognize it to be a shell and I'm going to plug and chug. That's great. However, I think some of you could have or did benefit from seeing this whole mess. All right, so let's see this in action. Volume generated by rotating the area between y equals 6x minus x squared and y equals 0 and around the y-axis. What I would like you to do is draw a picture of this scenario, please. So figure out what the graph of 6x minus x squared looks like. Figure out what y equals 0 looks like. If you want to graph it on your calculator, great. You want to use Desmos, that's great. But draw a picture of what we're looking at here. And don't forget the arrow to show what you're revolving around. So I'm going to talk a little bit while you're doing that. Most of you would realize that that's an upside down parabola. You might not know how the 6x affects it. Graphing it will give you a better picture of what's going on here. What is y equals 0 also known as? The x-axis, correct. Okay, so we got it? Yeah? All right, should look something like that. So the blue region is the stuff that we're talking about, and we're going to revolve that, we're going to revolve that around the y-axis. So what I don't have is this guy here. And I'm going to do this as a shell. Why am I doing it as a shell? Because we're talking about shells. Could I do this as a washer? Yes. The problem is, if I do it as a washer, I would have a horizontal rectangle. And if the rectangle is horizontal, do I work in y's or x's? Y's, which means I would need to solve this function for x. I don't know how to do that. So it kind of forces me into using a shell. Okay, so we need two things. We need the distance that the representative rectangle is away from the axis of revolution. This one's easy, it's x. And we need the area of that rectangle. Well, the rectangle is base times height. Here's the height. There's the base. Almost done. Where are we taking rectangles from and to? In other words, what are my limits of integration? Zero to 6. Okay, so let's put all that together. Height of the rectangle. Area of the rectangle. Again, we want a very, very, very skinny rectangle, even though it looks like a regular rectangle in the picture, who cares? Distance away from the axis is x. Well, how do we know that? I chose to put this rectangle there. Well, where's there? There is x. I chose it to be x. Well, how do I know the distance from the axis is x? Because again, right minus left, x minus 0. Well, we're not going to keep doing x minus 0 because we don't need to. But when I move that axis of revolution, it's going to become relevant. Okay? Put that all together and we get that part. This is a type of problem you would see on a non-calculator part of the test because it's a fairly straightforward integral to do. However, I don't really care about that now, so go ahead and int that. Tell me what you get for an answer. We'll see if you make the mistake that most people make when they're doing these problems. Notice you could use the function as x times the quantity 6x minus x squared, or if you're feeling saucy, you could do 6x squared minus x cubed. It's the same thing. Answer?
678.5.
Seem to have a consensus there? Okay. Well, I did it by hand, and I don't have an answer, so I'll trust you. Sounds good to me. You have an honest face.
Okay.
Okay.
What's like the mistake that people
Oh, common mistake that people make is they don't multiply the answer by 2 pi. So they'll f and int it, and then just stop and forget to multiply by 2 pi. The same mistake we saw when we did this in washers. People forget to multiply the answer by pi. Okay. Question?
I'm so confused on why the distance from the axis is just x.
Because that's where I chose it to be.
So you could. Okay.
So I could have chosen to put it over here
Okay.
if I wanted to. Well, where is that? It's just some random distance. X.
Okay.
Okay, so think of it this way. If you're doing a geometry problem where I say to you, I've got a rectangle where the base is twice as big as the height, and the area is 48. Find x. You know, you would do something like, well, the base is twice as big as the height. I don't know how big the height is, so let's call that x, and therefore the base would be x.
Okay.
Okay. Same thing is true here. I need to put a representative rectangle in there. Where am I going to put it? I don't know. There. Well, where's there? It's at x. Your x might be different than her x, might be different than his x, but it's still all x.
Okay.
Make sense? Okay. Any other questions? All right, so let's change things and make it more interesting. Let's do 2 things. We'll make a more interesting shape, and we'll change the axis of revolution. I did realize this morning that I had a typo in this, and I was too lazy to fix it. Problem solved. Okay, so this one I'm going to go through a little bit slower because stuff changes. I've got this green line that's intersecting a parabola, and it's creating a bounded region. Remember that term, bounded region. It's got to be a finite area. And I want to revolve that around the axis. We've done problems like this as washers. And you could do this as a washer problem. It would require 2 different integrals. It would be a pain in the butt when you got down here, but it's doable. If you grasp this shell idea, it makes the problem quite a bit easier. Okay? So, going through the same process that we talked about using that self-talk, is my representative rectangle horizontal or vertical? It's vertical, and therefore everything is going to be in terms of x. Is it parallel to or perpendicular to the axis of revolution? It's parallel. Boom, shell. So in your chart, you should have that formula that was in the orange rectangle on that previous slide for the formula for a shell. Okay, so I need 2 things. I need the area of the rectangle, and I need the distance away from the axis of revolution. So let's do the easier one first. What's the area of that blue rectangle?
X plus 4 minus x squared plus 2.
Good, let me stop you for a second. The height of the rectangle
Yeah.
would be what you just said, because it's top minus bottom. Good, okay, and how wide is that rectangle?
dx.
Perfect. Okay. So again, if I didn't have it listed in the picture, it would be top minus bottom, green minus red, x minus 4 minus parentheses x squared plus 2. Okay. And its width is dx, and so we have the area of the rectangle. Now the hard part. How far is that rectangle from the axis of revolution? This causes problems all the time, so I'm going to suggest to you to use the KISS method. Keep it simple, stupid. We want to know this distance. Now, back to what I talked about with Kaylee. How far is that distance? X. Good. Why X? Because I chose it to be X. I put it there. Therefore, how far is the rest of this? Again, stay with what we've learned. Now we're talking about right minus left. Okay, on the right is 5 minus the left, which is X. So its distance from the axis of revolution is 5 minus X. Now, you could approach that from a calculus standpoint, or using a calculus method like we talked about, right minus left. Or you could use logic. If this whole thing is 5, and part of it is X, then this remaining part is 5 minus X. Whatever works better for you. Whatever helps you get to that 5 minus X. I don't care. As long as you can figure out that that's 5 minus X. This one's a little bit different. It's not so obvious other than the fact that I put them on the picture, which I shouldn't have done in hindsight. You would have to find those points. Because notice they're not given in the problem. But you're all fairly bright and you could do a points of intersection, no problem. Again, if you don't have the quadratic formula on your calculator, you need to get it ASAP because you don't want to spend time factoring quadratics like I did. You just want to plug and chug into your quadratic formula and have it spit out the 2 answers.
So is the distance between the representative rectangle and
Mr. Reed?
y-axis, is that always x, the distance?
Yes, because we choose it to be there.
Okay.
Okay.
So we should always make that x.
I hate to use terms like always, but yes, most of the time you're just going to call that X.
I'm still just a little struggling to understand why it's 5 minus x.
Do you understand why that's X?
Just because we decided it is.
Okay, so let's, again, if I have a segment and the whole segment is 10 units long and I make that part of the segment X, how much is left?
10 minus x.
Yeah. Okay. I take a 10 meter segment, I snap off 2 meters, how much is left? 8. How did you get that? 10 minus 2.
Okay, I get it.
Okay. Yes, Marcus?
Yeah, I'm a little confused, like, about the dx and why that's always going to be the y value, how that works.
This dx? Whoops.
Yeah.
That dx represents the width of the rectangle. It's an infinitesimally small value because we want a really, really skinny rectangle.
Okay, and that's always going to be the y value for, like, these kind of problems?
Again, I hesitate to use terms like always, but yes, if my rectangle is vertical, then I will have dx as the representative rectangle's width. If my rectangle is horizontal, then dy will be my rectangle's width.
Oh, okay.
Because it's got to be really, really tiny. Okay? Anything else? Okay, now we put all the puzzle pieces together. I've got the area of the rectangle. No problem. I've got the distance from the rectangle to the axis of revolution. I now have my limits of integration. Oh, by the way, are my limits of integration from 3 to 6 or negative 1 to 2? Why?
Because that's where the bounded region is, and the other part's gonna be the 2 to 6 is gonna be the whole of the shell. Of the inner part.
Okay. I'll come back to you in a second. Yes, sir.
Just because it's rotating around the vertical line.
Okay. Now, those aren't incorrect. I was looking, I guess I'm asking a question I'm looking for the answer for. And the answer is vertical rectangle, like I said, everything is in terms of x. So my functions are in terms of x. My limits of integration are in terms of x, which tells me take the x value there, take the x value there. Okay? Yes, yes. Mine, I think, is a little easier. Put all that together, and we get that monster. Ooh, and that is ugly. Calculator part of the test. No problem. FN int. Non-calculator part of the test, not fun. Because now I've got a binomial times a trinomial. I have to multiply it out and solve. So I don't remember what I did. Oh, I think I actually, I multiplied it out because I'm silly. But that's not bad. You could do this. It does get a little tedious when you've got 4 terms. You have to take the antiderivative of each of those 4 terms, plug 2 into each of those 4 terms, plug -1 into each of those 4 terms, and then remember to multiply that whole mess by 2 pi. So I would probably FN int that, which I didn't do. Again, the answer is not relevant. It's getting to the setup that we're more concerned about. Okay, how are we doing so far? Cameron?
I understand if it's like a vertical rectangle that is in terms of x and like vice versa, but like how do we know it's a vertical rectangle like horizontal picture?
You choose. You're not going to like this answer.
Okay.
It's your choice.
Okay.
So if I give this problem to everybody, one of the skills you're going to have to develop is how you want to approach the problem. So if I go back to this initial picture and I say, you know what, I don't know, I'm feeling a horizontal rectangle, and I do this, that's great until I get to this little guy. Because once I get to that point, now all of a sudden my horizontal rectangle changes. And now I need 2 of them. And I don't want to do that. I can, it's just going to get ugly. For 2 reasons. Number 1, everything's got to be in terms of y. And number 2, now all of a sudden I have 2 integrals. So then I would say to myself, no, I don't want to do that. I'm going to use a vertical rectangle. That's the first decision you have to make. And you might very well get to the point where you go, all right, let's go. I'm vertical rectangling the snot out of this thing. And you get into it and you're like, whoops, that ain't going to work.
Okay.
Okay?
Yeah, thank you.
I know it's not an answer,
No, that's okay. It makes sense.
but you'll get better at it with practice. Okay? And sometimes it'll be obvious. I don't want to use the word obvious. Sometimes the problem will help you with that decision, like in this one, when you go back to the beginning. No, this one is okay. It was this one. I don't know how to solve this for x. So it kind of says, all right, you got to use a vertical rectangle then, because it's already in terms of x, just leave it alone. This one, I can solve this for x. Be plus or minus the square root of y minus 2, and I can go with that. It's just going to get really nasty, because I got a plus and a minus, and you got a plus on this side, you got a minus on that side, and then you got this business okay? All right, so last example. You can almost see where this is going by the way the equation is written. So we're going to do a little sidebar here. And that is, I have no idea what 2y cubed minus y to the 4th looks like. And I don't even know how to type it into my calculator. So I'm going to show you a trick to figure out what that looks like. And that is by graphing this. Whoops. Graph that function and see what it looks like. Okay? You got that little weird looking pseudo parabola looking thing? How does that tell me what this is going to look like? So let's do a little experiment. Suppose I had x equals y squared. For some reason, I have no idea what that looks like. So we're going to use the same method I just said. Well, I'm going to graph this. How do these two graphs compare to each other? Well, you know what this looks like. That's a right side up parabola. What's this look like?
A sideways parabola?
Sideways parabola, correct. So these two things, by switching the x and the y, you're looking, you'll remember when we did inverses, you're looking at a 90-degree turn. So this graph that you're looking at on your calculator, the actual graph will be that same thing turned 90 degrees.
90 degrees, which direction?
Counterclockwise. No, clockwise. Oh, wait, clockwise, go that way, yeah. So after that long verbose discussion, we get that thing. Now, there's some other parts in here. That graph on your calculator's got another little hump looking over here, and this extends into that way, but I don't care because I'm bounding it by the y-axis. So that's the shape we're dealing with. Even though I have a horizontal rectangle in there, let's start it from scratch. Let's pretend that's not there and address Cameron's concerns earlier. If I just dive into this problem, and by the way, I'm going to revolve around the x-axis, so I'm doing that. I would like to be able to do this as a washer because I like washers better. In order to have a washer, I'd have to have a rectangle that's vertical. A lot of times when your rectangle goes from the function to the function, in other words, from one function to the same function, that's going to cause problems. And how else is this going to cause problems? Well, like I said before, I don't know how to solve that for y. Looking at those couple things, that tells me all of a sudden that I'm going to have to use a horizontal rectangle. And so we go back through the flow chart again. Horizontal rectangle, everything's in terms of y. Is my rectangle parallel to or perpendicular to the axis of revolution? It's parallel, and therefore we're doing shells. Okay, which is kind of silly because it says at the top of the slide, use shells, but you're not going to always have this availability when you're doing these problems. You'll just be given the problem and you have to figure out what to do. Okay? Beautiful. All right, what's the area of that rectangle? I'll give you part of it. It's right there.
Dy times 2y to the third minus y to the fourth.
Perfect. I'm going to write it even more simple. Simpler. I don't know, whatever. Right minus left. So 2y cubed minus y to the fourth minus 0. Staying with that whole right minus left thing. But you're all smart enough to realize that we don't need that. Now, why do I keep doing that? Because if it's not something pretty like one of the axes, you have to be able to do that. Okay, so very good, times dy. We're good to go. How far is my rectangle from the axis of revolution? Y. Perfect. And I'm taking rectangles from where to where? We're almost done here. I just need my limits of integration. 0 to 2. Not 0 to 0. That makes no sense. Because again, everything's in terms of y. 0 to the y value, which is 2. Put that all together, and we get that puppy. Let's practice just to make sure you can do that. Fn int that, please. I don't think I have an answer, so I will do it also. Anybody?
13.4.
Yes, I got the same thing. Good, 13.4. Okay. Now, why did I have you FN int that? Number one, for practice, but also, I think I mentioned this, in fact, I must have mentioned this already. If you have to FN in something in terms of y, you can just do it in terms of x because it'll give you the same answer. Okay? Questions about this guy? Beautiful.